code. Now this ID I know, right? And GM I know here. So GM is equal to 2ID divided by BGS minus VTH. In terms of the parameters, I know how much is this. 2 times ID is 11 upon, or let's keep it in this manner only. 2 times VDD plus VTH upon RL minus VB upon RL. This is our ID divided by VGS is how much? VB minus VTH. Okay. This is equal to, much easier step would have been even simpler using this value to replace. So 2 times VDD by RL minus VB minus VTH upon RL divided by VB minus VTH. Okay, so how much is this? 2 times VDD by RL into VB minus VTH, correct? And minus of how much? 1 upon, sorry, 2 upon RL, correct? Right? Yes, so this should be equal to how much? We know that GM is equal to, already found 1 millisiemens, right? Has to be 1 milli. So solve this. How will I solve this? Send RL to the opposite side, right? So 1 milli into RL. RL is 60K. So K and this one go away. 2 VDD. And also take VDD here. 2 here. So 2 upon VDD upon VBB, VB minus VTH minus 1. Okay. This becomes 30 is equal to, so this becomes 31 VDD minus divided by VB minus VTH. So how much will this be? So VB minus VTH will be equal to VDD upon 31, correct? So VB will be equal to VTH plus VDD upon 31. How much is that? How much is this equal to? So 1 volt plus VDD upon 31. So what is VDD? 10 upon 31, right? This is the voltage. If you have this VB, then you will be having a gain of how much? 60, right? Got the point? Let's see if we have made any mistake or not here in the calculation. So this is fine. It's a very good practice. Always after solving something, just check it once whether you have made any mistakes or not in the calculation. So 60 by 60K, so the GM is fine. It's needed to be 1 millisiemens, right? Earlier what was the GM in the previous question? It's 50 microsiemens. So yes, fine. Now the next thing is that what is the current? The current is 2ID by GM is 2ID by VGS minus VTH. This is fine. Okay. All right. And from here you found out what is the value of ID. ID is equal to VDD minus VDS upon RL, right? And VDS is how much? VDS was equal to VB minus VTH. So you put that here, VDD minus VB minus VTH upon RL. Then 2ID you have replaced VB ID you have replaced with this particular equation here, Vd by RL minus V minus Vth by RL. Okay, after that what did we do? GM value we know from here, 1 millisiemens. Okay, and here we have replaced two, so we have taken these two separately. Okay, so 2 VDD upon RL into VB minus VTH minus 2 by RL, right? So this is fine. After that, what did we do? We took 2 over RL, we multiply both sides with RL over 2. So RL over 2 multiplied both sides. So this is VT by VB minus VTH, and this is minus 1. This is RL over 2. So RL over 2 is how much? 60k by 2 is 30k. 30k multiplied by 1 is 30. Then we took 1 from this side to this side, so it becomes 31. So this is fine. VD by VB minus VT is fine. VD by 31 plus, yeah, so it is fine. So how much VB do you need? How much value of what is the value of voltage that you need? VB should be this particular value, right? For the incremental gain to be equal to incremental gain to be equal to minus 60, right? Did you understand this? How to solve? What did we do?
Yes.
Yes. Now tell me, we in all of this, in doing all of this, we didn't actually find out what should be the transistor size. Yes, we didn't do that, right? We have not yet find out how what is the transistor size, W by L. So tell me,
Yes.
for this particular VB, and this particular current, what should be the transistor size? What should be W by L? Can you find out?
Yes.
So tell me, what will be the W by L? So we know ID is equal to, this transistor is definitely in saturation, right? So mu n Cox over 2 W by L into VGS minus VTH square. Yes?
So we don't need to check whether this is saturation or not.
We have actually applied the condition, right? Of
We have,
saturation here.
yes,
We have
we did.
actually, yeah, you need to, you should check, but actually we have derived everything with the condition only, right? The condition is that, first of all, the condition was here itself, right? This is the condition that we have applied here, right here.
Yes.
Okay. Okay, you can also check it once. It's not a problem. So VB we have found out, yes? So what is the current because of this VB? It is here, right? So what is going to be the current? Tell me, what is going to be the current here? ID is equal to how much? VDD by RL minus, oh sorry, 11 by 60k minus VB by 60k, which is 1 plus 10 over 31 upon 60k. This is ID, right? So this is how much? 11 minus 11 by 60k, or rather 11 minus 41 by 31 upon 60k, right? So how much will this be? This may be something, this gives a very weird value, right? So it's difficult to calculate, but it will be something, some positive number, right? ID is positive. So that is first sanity check. ID is positive. Now what will be ID times RL? So basically what is VDS is equal to VDD minus ID times RL, right? How much is that? So VDD is 10 volts minus ID times RL. So ID is how much? 11 minus 41 by 31 divided by 60k times 60k. Isn't this go cancel away? 10 minus 11 plus 41 by 31. How much will this be? 10 upon 31, right? 10 upon 31 volts. And what is so this is VDS, right? And tell me what is VGS minus VTH. So VB is this much, right? This is VB. So this is VB minus VTH. So how much will this be? VTH is equal to 1 volt, right? So if you subtract 1 from this one, you'll again get the same thing, right? So these two are equal, right? Which means that the transistor is biased at the edge of saturation, isn't it? Am I right? So this is assumption is fine. Now I wanted to find out W by L, right? So ID I have already found out here. Sorry, here. And from the equations I know everything. So except for W by L. So W by L equal to how much? ID upon VGS minus VTH whole square 2ID, right? Upon mu n Cox. So replace everything here and you will get W by L. Okay, that's it. So that is all that I wanted to discuss. So any doubt in this question?
No.
Yeah. So I think that is all which I wanted to discuss today. If you have no other doubt, then probably we'll just conclude the session. So there is another problem number 2, which I would like you to solve it for yourself. It's the same kind of a problem, just there is a small change here. I have placed a small resistor RS at the source. Then I want you to do some calculations here. Yeah, so good. In that case, just there's no other doubt, then we'll meet again probably in the next session probably.
Yeah, I have a doubt in the assignment.
Yeah,
Basically, not on the not on the question itself, but you provide a hint there.
4, right?
Yeah. So consider the circuit shown in the figure where it is. Yeah. Oh, so yeah. So it just after question number two, with question number two, I think.
This one.
Yeah, that hint.
Do you want to?
Yeah, just click on that hint.
Okay.
Yeah. So it says assume VB is at the maximum possible value.
Hmm.
So it is. So is
While
it?
keeping the transistor in saturation.
No. My question is,
Hmm.
uh, what does it mean? VB is at its maximum. So is it already maximum possible value, or you are asking whether find the maximum possible
So
value?
question is, what is the value of VD? Okay, when the transistor M1 is at the edge of saturation and linear region. That is the question, right?
Yes.
They want to find out what is the value of VD, right? At the drain,
Yes.
correct? But for that, for calculating that, you need to have some information about VB also, right?
Yes.
Correct. So
Yes.
that is the hint here. That assume VB is at the maximum possible value such that the transistor is in saturation. You know that already, that if the VB, I already discussed this today, right? That if all other parameters are fixed and if you keep increasing VB, there will come a time when the transistor will go out of saturation, right?
Yes.
Right? So
Yes.
there is a maximum possible value of VB for which the transistor will still remain at the edge of saturation, right?
Yeah.
Yeah, so that is what is being told here as a hint. You have to assume that VB is at the maximum possible value. when the transistor is still at the edge of saturation. Got it?
I understand your discussion. That is completely fine, but not actually this question.
I
I
mean,
don't
like,
know. Okay, let me again think.
no, no, see, what I'm saying is, VB, when you increase VB,
No, there in your discussion, so you already calculated VDS, right? We already know
yes.
the VDS, IDS, and everything, all
Hmm.
other parameter.
Hmm.
And then you are saying that we know the it is saturation. Now check the whether what about VB, how it will behave.
That is one possible question that I framed. So the thing is here is that they have not given anything about VB, right? They have not given the value of VB, but it is not required because they have already told that assume VB is at its maximum possible value while keeping the transistor in saturation, which means that there will be a, there cannot be a lot of values of VB, right? For that, there is only one possible value of VB where the transistor is at the edge of saturation, isn't it?
Okay.
That you can find out. If you put
Yeah.
the condition that the transistor is at the edge of saturation, then you can find out that, because that is where the maximum where the VB will be maximum.
Yes.
Okay, so
Okay.
try this out on your own. You will
Yeah.
be able to do it. From the
Thank you.
discussion that we had today, I am sure you will be able to do it.
Yeah. Thanks. It's a very elaborative one.
Yeah, welcome. So we'll again meet next Tuesday.
Sir, can you display the second question so that I can take the print?
Which question?
You solved. No? You told that to do by us.
Oh, I will upload anyway the lectures today or tomorrow.
It's okay. I have taken the print screen.
Okay,
Okay, sir.
fine. All right,
Sir,
sir.
can I ask a doubt from week 3, sir?
What is the doubt from week 3?
Sir, in module 8, actually in week 3, module 8, I have a doubt on the topic, sir.
Yeah, what is the topic?
Here in the MOSFET as a
Your
two-port
voice
network,
is
right?
not audible.
Sir, we have framed MOSFET as a two-port network, sir, in MOSFET 8, right, sir?
Yes.
Sir, in there we have plotted I2 equal to beta V1 minus VTH square now, sir.
Where?
Next page, sir. Next page. Yes, sir. When the equation came, sir, I2 equal to beta V1 minus VTH whole square.
This is not the one, right? This is the one that you are talking about. This page only. Correct?
Yes, correct, sir.
So,
I2 equal to V1 minus VTH, that equation, sir.
yes, yes. So,
I have doubt, how did that equation came, sir?
oh, that equation. Okay, don't worry about this. This comes from device physics. This is something which we do not need to understand. For us circuit designers, we only need to know what is the current equation. That's all. Okay, just take it for granted.
Okay, sir. Yes, I have no problem, no, sir. That means if I don't need to derive it or something,
No,
no,
you do
no
not need to
need,
derive
right,
it
sir?
because this is known to you. As circuit designers, we are given some device, okay, and we know how the device behaves, and then after that we build something using that device. That is where the circuit designer's creativity comes in. Okay, as circuit designers, we do not need to find out how the device works. Okay, that is someone else's job. As circuit designers, our job is to find out, our job is to design something given that given that the device works. That's all. Okay, that's all, nothing else.
Sir, thank you, sir. Thank you, sir.
Yeah, all right. So then I will conclude the session today. We'll meet again on next Tuesday. Okay, till then, study.
Okay, sir. Thank you, sir.
Thank you, sir.